So good afternoon. It's a pleasure to be here. zSpace builds an interactive 3D virtual holographic workstation for a user that is really immersive. It's very realistic. It feels incredibly realistic. And I'm going to be describing the system today. Now, before we actually describe the system, I'd like to sort of set the context and explain what does it mean when something is immersive. And certainly, we're at a 3D display conference. The display itself is important, but there are many other factors which are really important that creates a truly immersive experience. Now, what does immersive mean? The founder of zSpace is a cognitive scientist, and he likes to use this term, cognitive levers. What is a lever? I'm sure all of you guys have seen this or heard of this very famous quote from Archimedes. Give me a place to stand with a lever and I can move the world. Meaning, it's a very small thing when applied at the right place with the right amount, it can move mountains. What's a cognitive lever? A cognitive lever are those things in our cognition, in our perception, that activates our brain. So basically, if there's something that's really small that you catch maybe in the peripheral of your vision or in your body or you hear or you smell, something like that, it really triggers that aha moment. And that aha moment is when all the little gears line up in your head and you say, oh, I'm looking at something real. So we believe that there are these levers in your brain that really trigger the spatial, the analytical, the intuitive aspects of your head and of your brain. And some of these levers that we'd like to call cognitive levers are here. Certainly, the second one we've been talking about all day, a really good 3D display, stereoscopic display, will give you that sense of immersive experience. Really great 3D graphics in applications. This is SD&A, of course, so applications has got to be part of it. Providing motion parallax. We've heard that a lot, whether it's horizontal motion parallax or vertical motion parallax or coming in and out. To have motion parallax, even without stereo, is incredibly powerful. Another cognitive lever. And I'm going to talk to you a little bit more about the proprioception. This is a cognitive lever, which is how you know your body exists in space. I know that my right hand is here, my left hand is here, it's tilted at this direction. That's proprioception. And that is also an incredibly powerful cognitive lever. The thesis of our company is that if you engage a collection of these levers in the proper sequence with a proper mix, the user experience becomes very, very immersive. It becomes real. So that's the context of cognition and immersion. Now, what is our system? The zSpace system consists of the following parts. First of all, there's a full color HD display, stereoscopic display. Matched with that is a pair of very lightweight polarized glasses. And they're tracked. It says they're tracking eyewear. How are they tracked? They're tracked by some tracking cameras that are built into the bezel. You can see a little bit of it there and there, tracking cameras. In addition to that, as I mentioned about proprioception, manipulating with a user input is really important. And for that purpose, we provide a really unique stylus that allows you to interact with the virtual objects directly, shall we say. And then finally, on top of that, we provide a very innovative software development platform on which you can build incredible applications. And I'll show you some examples of that later on. The combination of all of these triggers the user to say, oh my gosh, this looks real, this feels real. I'm looking around objects, I'm interacting with objects. And so I'll show you a little bit example of how people react to zSpace when they first play with it. What you're seeing is a augmented reality version of it. You can produce it in real time, but the person wearing the glasses sees everything in 3D. This shows that you can collaborate through a network of zSpace systems. You can interact with it with your 3D stylus. It looks so real, people are just shocked, like this. So how do we do that? So let me now describe the various components of the system. We'll start with the display. The display is a 24-inch display. It's custom built for us at Z-Space. You know, there is a TN display. There is a segmented backlight, and then in front of the TN display is a polarizer switch, a polarization switch. Let me briefly talk about the polarization switch. What is it? Well, it's a TN cell, just like the LCD is. If we subject the TN cell to a low voltage, it induces, after the quarter wave plate, a circularly polarized light. In this case, is for the left view. And similarly, if we, for another frame, we turn it to high voltage, it lets the light go through the quarter wave plate, and what we get is the other circularly polarized light. So counterclockwise versus clockwise. And one of them goes through a left lens, and one of them goes to the right lens, like this. So then the left eye will only see the left image because the circularly polarized light will go through the left lens and gets past to the user. The right eye will see essentially nothing because it's polarized, circularly polarized the wrong way, so it's just blank. And then similarly, when it's time for the right image to come in, one frame later, the right eye sees this image and the left eye sees essentially blank. And we just swap back and forth. So that's time sequential using passive polarized lenses. Now, one of the problems with using time sequential displays is the fact of progressive scanning. That we display an image, let's say we display the left image, a row at a time, starting from the top, and then we sequence down. And then we write the right image, a row at a time, starting at the top, and we go all the way down. So what kind of problem does that cause? Well, let's imagine you're looking at this time, this point in time. What image is actually on the LCD? Well, on the bottom part, it's still the left image because we haven't started writing the right image. The right image we start writing right here. So let's say we start writing right here, and at this point in time we've written this segment, maybe we've written this portion. So this top half, we're seeing the right data. However, on the bottom half, we're still seeing the left data. It's left over from the previous time, and we haven't gotten around to writing it. So when you look at it in this instant in time, what are you going to see? You're going to see a mixture of left and right images. And once that's on there, your brain sees it and you can't pull it apart anymore. So what do we do? Well, we have to hide it. We have to hide the fact that part of the image is for the right eye and part of the image is for the left eye. And we hide it by using a segmented backlight. So here's what we do in our system. We segment the backlight into, it turns out we have 5 segments, even though this picture only shows 4. Nevertheless, so the left image is written one segment at a time. So it's written right here for the first portion of the frame. And at the same time, we turn on we know that it's going to take a certain amount of time, 3-4 milliseconds, before that image is stable. And the same thing happens with the polarization switch. We turn it to the left, we turn it for the left eye, and we set the polarization switch for the left state. However, we hide it. We don't actually turn on the backlight until both the polarization switch and that segment has settled down, after this amount of settling time. And at that point, we turn on the segmented backlight. We turn on the LED just for that burst. For the rest of the time, that LED is off, so you don't see anything, so we're hiding the mixture, shall we say, and we turn on the LED just at that little spot. And then we turn it off, and then we write the right image. And similarly with the right polarization gradient. And then we turn on the LED right at the last minute, and we pulse it. And we do that for all of the segments. So we actually just pulse it, segment by segment by segment, sequenced in time, so that we only see the correct image at the correct time for a brief second. So that's how we deal with separating the left and right carefully and well to minimize the effect of ghosting. So that's a display. Let's talk a little bit about the tracking itself. We need to track so that we know where the left and right eyes are, right? And the way we do it is we use optical tracking, and I'll just briefly tell you what we need to do. For tracking, we need to give the left and right eye, we have to tell the position as well as the orientation, the yaw, pitch, and roll of whatever target that we're using, we're tracking. Together, the position and the yaw, pitch, and roll gives us 6 degrees of freedom that we have to track. And we use very simple, conceptually simple idea of triangulation. We have 2 cameras that look at a particular point out in space, let's say my left eye. And using a little bit of geometry, we know the distance d, we know where that left eye is by measuring the angles alpha and beta, and a bit of geometry and a miracle occurs, we solve for the distance z. And then we can also get all the distance x and y similarly. So we do that for a number of points, and we can get the position, the coordinates, x, y, and z for any target, not just your eyes. That just gives you x, y, and z. Now what do we do about the yaw, pitch, and roll? We take advantage of the fact that any 3 non-collinear points determine a unique plane. And we measure 3 points of any object with respect to some reference point, let's say the upper right-hand corner of this picture, and what we get is a rotation matrix that represents exactly the plane of those 3 points to our origin. And that gives us the yaw, pitch, and roll. The system that we use is this way. We have reflectors that are located right on the glasses, because we have to wear glasses anyway. We illuminate the reflectors with infrared LEDs, and then we look at the reflections through an infrared camera built into the bezel. And then we do some post-processing, some triangulation, and we get the images properly. Just as an idea of what happens when you combine head tracking with real-time rendering, this is what happens when you don't have any motion parallax, and this is what happens when you have motion parallax. Even in the absence of stereo, this is incredibly immersive. It gives you a sense of depth that you just can't get anywhere else. So that's the first thing. Tracking of glasses gives us motion parallax. Now I mentioned that you can also use a unique stylus to pick up and rotate and manipulate objects. How do we track this stylus? Well, we do it partly also with optics. We're also looking at the front and back tips of the stylus. But the stylus has to be very accurate. For proprioception to work, every millimeter you move, every 1/10 of a degree you twist has to be detected. In order to get that kind of rotational accuracy, we also have to track using rotational MEMS sensors. So we put in a gyroscope and we put an accelerometer into the stylus. And we measure the angle of rotation as well as the direction of gravity to resolve for any ambiguities. And we fuse that together with some Kalman filtering with optical tracking, and we get an incredibly accurate 6 degree of freedom tracking of the stylus. I'll give you a quick idea by using a video of what that can give you. So here is we can pick up a heart, twist it, 1 for 1. I move 1 millimeter in my hand, and the heart moves 1 millimeter. I twist it. The stylus also has multiple buttons, so I can use different buttons to, say, turn parts of the heart transparent. I can also choose a different tool. In this case, I choose a 3D spline tool, where I sort of build a 3D, I don't know, a roller coaster, you might say. And wherever my hand moves, I can drop a dot. Now you combine that 3D manipulation with motion parallax, and I swear, it feels like you're dealing with a real heart. It's incredibly, incredibly immersive. An application where such a combination of motion parallax and direct manipulation is EchoPixel.
To an angle or a view that's interesting. Pick it up and turn it in any way that I want to explore.
So this is an actual scan of a 12-year-old girl, and that scan has been filtered with some density filters, and you're actually looking at her torso in as she manipulates. And Beth is putting exactly the right view you want.
There. Then I can take the
And then she
cut
can
plane,
pick up the slice.
and I can look at them from the side and cut off the extra parts.
The slice plane could be moved in any way you want, in any orientation, in any position.
Or bring in more tissue if I'm thinking I lost something.
Wow. So that's an example of the power of direct manipulation and the power of proprioception in conveying a sense of realism. So my time is almost up, so let me give you my conclusions. So I presented a stereoscopic system, and I stress the word system. It's not just a 3D display. We talked about its segmented backlight, which minimizes ghosting for stereoscopy. We talked about how optical tracking of the glasses allows you to do motion parallax in all 3 dimensions. Optical and inertial tracking of the stylus then gives you direct manipulation of the object, and really compelling software that creates imaging, medical imaging, education, simulation, computer-aided design, all sorts of applications that sit on top of this platform. And so a combination of these optical, inertial, cognitive, and perceptual cues then create an incredibly immersive user experience. It's lifelike, realistic, and very, very interactive. So that's our Z-Space system, and as Greg mentioned, I will bring a system tomorrow afternoon, so come to the demo session in Ballroom 4, and you can play with it yourself, and hopefully we'll elicit a wow from you. Thank you for your time.